Today we are going to discuss about equivalent and approximate equivalent circuit diagram of a transformer. As we know, transformer is a static device which can transfer electrical energy from one circuit to another circuit by changing the level of voltage. Here if input voltage is V1, the output voltage is V2. To draw the equivalent circuit diagram of a transformer, we are considering the primary winding is having a resistance R1, the leakage reactance of primary winding is X1. Though there is a core and core parameters are represented in parallel, and this is RC, this is XM, where RC represents the resistance of the core and XM represents the magnetizing component of reactance due to which flux is developed in the core. The EMF developed in primary winding is E1. Now, this is the primary side parameter of the transformer. Considering the secondary side, in case of secondary side, secondary winding is having a resistance R2 and the leakage reactance as X2. The current flowing in the secondary winding is I2 when some load is connected across it. However, when there is no load, the current in the secondary side will be 0. Here, if we summarize all these parameters, V1 and V2 are the primary or applied voltage, secondary or output voltage. E1 and E2 are the back EMF in primary and secondary winding. N1 and N2 are the number of turn in primary and secondary windings. I1 and I2 are the current in primary and load or secondary windings. I1 dash and I0 are the counterbalance and no load current in the primary side. Counterbalance here means if there is some current in the secondary side, in counter of this secondary current, there will be extra current will flow in the primary. That current is known as I1 dash. However, when there is no load in the transformer, then only I0 current will flow, and this current is known as no load current. This current having a two component, one component is flowing in the resistive part of the core, another component is flowing in the inductive part of the core. The resistive part of the component of current causes heat loss, whereas the inductive part of the component of the current, no load current, causes flux in the transformer core. Now, considering the secondary and primary, the resistance of primary winding is represented as R1 and the resistance of secondary winding is R2. The leakage reactances in primary side is X1 and in secondary side it is X2. Whereas RC is the core resistance and XM is the reactance of the core of the transformer. Now, this is known as equivalent circuit diagram of the transformer. This equivalent circuit diagram can be replaced with an approximate equivalent. Here, there are two representations of transformer. One it is equivalent, another it is approximate equivalent. In case of equivalent transformer, the primary parameter winding parameters are represented in series with parallel combination of core parameters, whereas the primary parameters of the winding is represented after parallel combination of the core parameters in approximate equivalent circuit diagram. This is the major difference between the two. Now, why we represent these parameters prior to this R1 and X1? Because when V1 is applied directly across Rm and Xm, we can easily analyze the current flowing in these two paths, and we can analyze I0 without having any calculation part of X1 and R1, E1, etc. or the rest of the circuit. We can analyze this network as a separate parallel circuit, and hence it makes our calculation easy. That is why it is known as approximate equivalent circuit diagram of the transformer. Why it is approximate? Because no load current I0 is hardly 8 to 10% of full load current, and hence this is considered separately. Now, considering this equivalent and approximate equivalent circuit diagram of the transformer can be analyzed at no load, whereas it can be analyzed at full load. Now, when transformer is at no load, the current in the secondary winding is 0. Now, if current in the secondary winding is 0, the counter current in the primary winding I1 dash will also be 0. When secondary winding of transformer is kept open, the transformer is said to be at no load. Now I1 dash is equal to 0, I1 will be equals to I naught because only the I naught no load component of current is flowing in the circuit and rest of the circuit is considered as unenergized. Now only Rm is having some current and Xm is having some current. The component of current in Rm is Iw and in Xm it is Im. Because this is considered purely resistive, this is considered purely inductive, and hence if flux is taken as reference, the current which causes flux, it will be in same phase with the flux, whereas the current which causes heat loss in the transformer, it will be at 90 degree with the flux. And Im and Iw are due to the reactive component and resistive component, and hence they are at 90 degree. The phasor sum of these two components is I naught, and hence we can say I naught is equal to Iw minus J Im. Here J represents the 90 degree phase displacement between Iw and Im. This is the real component, this is the imaginary component. Now Iw is from this phasor diagram. If this angle is, let this angle is theta naught, the Iw is I naught cos of theta naught. From the circuit diagram we can easily calculate this voltage is applied across Rm. The voltage we are knowing Rm, the resistance we are knowing voltage we are knowing V1, whereas resistance is Rm. Then we can easily calculate I using Ohm's law, V by R. Now similarly, if we are knowing the reactance of the second path and Xm, then the corresponding current we can easily calculate, that is V1 upon Jxm. Jxm is inductive reactance of this part of the transformer. This is no load phasor diagram of transformer and equivalent circuit diagram of transformer. Now the EMF, whether there is a load or not, the EMF in the primary side E1 and EMF in the secondary side E2 will develop, and they will lag this flux by an angle of pi by 2, because both the EMFs are developed due to flux only, and the flux is the common component in primary and secondary winding, causes mutual induction. Now when transformer is on load here means when I naught is not equals to 0. It means there is a load having an impedance of Z. Z may be of purely resistive, Z may be of purely inductive, Z may be of purely capacitive, or it may be a combination of R, L and C. Now when some current is flowing in the secondary side, there will be a counterbalance current in primary side I1 dash. Now due to this extra current flowing in the primary side, the voltage drop will cause in R1, and similarly voltage drop will cause in X1. Now the applied voltage, when we are analyzing this parallel circuit, the voltage across these 2 points will be V1, and we can separate out this Rm and Xm. We have already studied in no load case. Now we can find out I1 is equal to the phasor sum of I1 dash and I naught, and hence it is phasor sum of I1 dash and I naught. Now V1 is equals to what? The voltage drop in this resistance, voltage drop in this reactance, and the back EMF, the phasor sum of these three components. We know E1, the phasor of E1, then phasor of I1 R1, then phasor of I1 X1. When we have adding these quantities in phasor, then we can easily find out V1 applied voltage. Similarly, due to the mutual inductance, EMF mutual induction, E2 is developed in the secondary winding, and after this E2, when some current is flowing in the secondary winding, there will be some voltage drop in X2, there will be a voltage drop in R2. Now by subtracting these two voltage drop from E2, we can get V2. Similarly in this equation, if we can subtract this voltage drop from E2, the E2 minus I2 R2 minus I2 X2, and this phasor sum of these quantity we can easily calculate the V2. This is the significance of these parameters when transformer is subjected to some load and I2 is not equals to 0. Now, if cos theta 1 and cos theta 2 are the perfecto transformer in primary and secondary side, then the phasor diagram of transformer for inductive, resistive, and capacitive load can be drawn. Now, considering the on load trans transformer, when this is the phasor diagram when transformer load is inductive. Inductive here means RL. When transformer load is only resistive, having resistance only. The capacitive here means RC. The nature of load is RC, the nature of load is only R, the nature of load is R and L. Now, this is the equivalent phasor diagram of transformer. How here flux is taken as reference. This component I naught Im is in same phase with flux because of magnetizing component. This is IW as we have drawn in no-load diagram. The phasor sum of these two is I naught. Now, due to the current in the secondary winding I2, the counter current which is just opposite to I2, I1 dash will flow, and the phasor sum of I1 dash and I naught is nothing but I1. Now, if we want to find out the applied voltage V1 in the primary side by considering all these phasors, we know V1 is the phasor sum of E1 and voltage drop in resistance, primary resistance, and voltage drop in primary leakage reactance. Now, if I plot this diagram independently, then I consider flux as reference. As we know, this is only flux which is common in primary as well as in secondary. Let's consider this phasor E1 and this phasor is E2. This is E1 and this is E2. Now, the current which causes this flux is already considered as Im, magnetizing current, and the current which causes some loss in the transformer core is represented as IW. Now, at no load, we know the phasor sum of IW and Im is nothing but I naught. This is up to this point, this is the phasor diagram of transformer at no load. Now, when we know the some current is flowing in the secondary winding, let it is I2, and because of this I2, the extra current will start flowing in the primary side, and which is just opposite to this I2, and this current is I1 dash. The phasor sum of I naught and I1 dash is nothing but I1. Here we can say I naught is equal to IW plus JIM. Now, similarly, we can have I1 is equal to I naught plus I1 dash bar. This is also bar. Now, considering this phasor diagram, now we have to find out V1 and V2. We know V1 is what? E1 plus I1 R1 I1 dash plus J I1 X1 X I1 dash. V2 is what? E2 minus I2 R2 minus J I2 X2. Now, considering this vector is E1, if we reverse this vector E1, reversing this vector E1, then we can represent it is as minus E1. The voltage drop in resistance in R1 due to current I1 dash, it will be in same phase with I1 dash. This is I1 dash R1, and these two vectors are in parallel. Now, the another component I1 X1. I1 X1 will be at 90 degree with this resistive drop. It will be J I1 dash X1. This is the phasor sum of these three quantity E1, I1 R1, I1 X1 is nothing but V1. meet this value with center, and this is V1. This is what the KVL equation in primary side. Similarly, we can prove KVL equation in secondary side. We know this is the current in secondary winding. This is the EMF developed in secondary winding. If we can subtract these two vectors from E2, then we can easily find out V2. Now, if this is the current flowing in the secondary, if we subtract this quantity, which is these two are in parallel. These two are in parallel. This is I2 R2. But this, why we have taken this vector in this direction? Because we want to subtract this vector from E2. If we are taking this vector in this direction, it means we are going to add this vector in E2. But our requirement is to subtract this vector from E2. Now, drawing another phasor which is at 90 degree, that is J I2 X2 at this phasor. This angle is 90 degree. Up to this point, and this is meeting this point, this vector is now V2. The angle between V2 and I2 is theta, theta 2. Here this angle is theta 2. And why this I2 lacks this V2, and hence this is for an inductive load. Now, considering this phasor diagram, we can easily find out the phasor diagram for resistive load as well as capacitive load.